السلام عليكم ورحمة الله وبركاته. I'm going to solve the test 1 exam and clarify the doubts that some students have referred have referred and said or stated these are complicated. So for question number 1, if you see two-way shear is acting at a distance of d or 1.5 d from the face of the column. We said we have two types. One is one-way shear, another one is two-way shear, and we said some of you have got one-way shear, some of you have got two-way shear, and the correct answer here is 1.5d. So I'm assuming that this is a question that does not require a lot of time. Second thing, where you are asked to calculate the bending moment at the face of the support for the left column. Some of you have got it for the left column, some of you have got it for the right column. So if we see a moment, we said it's equal to W all square over 2, since it's a cantilever, where W is 200 multiplied by 2.7 square divided by 2. So if we open our calculator, 200 multiplied by 2.7 multiplied by 2.7 divided by 2. So our answer is 729 kilonewton meter, taking into account that I'm solving with you. Okay. Now question number 3 says for you. Okay, question number 3 says for you, according to the structural foundation schedule shown below, answer the question. The area of steel provided for CF2 for the top longer side in millimeter square is certain value. Okay. Now if we see the question, okay, if we see the question, okay. Now this is CF2, okay, and we are referring to the long bar in the top. So this is the top long bar where we are having it 14 diameter 150. Okay, so you can get it either by calculating by r square. Okay, so by r square, so by into 7 square, that's the area of one bar, multiplied by 1000 divided by 150, as I told you. Okay, where the answer is 3.14 multiplied by 7 multiplied by 7 into 1000 divided by 150, where the answer is 1026. Or you can use the code that has been given to you, okay, which I have told you to keep with you. So if we see here the last page, we are having 150 mm, we have 150 mm. Okay, so we have 150 mm, and then we have 12 and 16, we don't have 14. So what we can do, we can take the average of 754 and then 1300 and 1340. Okay, the average of 12 and 16 will give you 14. Okay, so 1340 754 divided by 2, which will give you around 1047. Okay, so going here, 1047 is accepted as well. Or for certain students who have calculated it for the whole width rather than calculating for 1 meter only, that answer is considered to be correct as well. Okay, now according to the structural foundation shown below, answer the question once again. The self weight, okay, the self weight of CF1 is, so we have, once again, this is CF1, this is 5 meter, so 5 self weight is 5 meter multiplied by 2.5, that's your width, multiplied by 500, which is zero point 0.5. And I have already explained for you these things, stating the length, the width, and the depth. If you remember, I have opened for you foundation schedule. Okay, now this is the volume to calculate the self weight. Okay, although that I have explained it in the earlier lectures on how to calculate the self weight of the different elements, but calculating the volume, multiplying it by 24, which is your unit weight of concrete, will give you the answer. Okay, so 5 multiplied by 25 by 2.5 multiplied by zero point 0.5 multiplied by 24, which will give you around 150 150 kilometers. Okay, so once again, 5 into 2.5 into 0.5 multiplied by 24, which is unit weight of concrete. Okay, so we have solved the first 4 questions. Now going for the other questions. Okay, so going for question number 5. Okay, going for question number 5. Question number 5 says for you, according to the basics of a combined foundation analysis and the figure of CF2 shown below, the column that tends to be having lesser load, some of you have got it lesser load, some of you have got it to be heavier load. Now, there are two things to be taken into account. Now, since there is no load, okay, so since there is no load, you can use your common sense or your logic, or you can refer to the question that we have solved together, where your handouts, where your videos are there, and my solution is available. Okay, and you can notice if you return back to my videos, you can see eventually that the column which is having the higher load is going to have a higher edge. Okay, so it means if we are referring that this is a higher load, okay, this is a higher load, the width here is going to be something bigger than the other column. So if we are referring to C1 and C2, C1 is having 1.3 from the center of the column to the edge, the other one is having 1.5. So by common sense, C2 requires a wider length to the edge. Okay, so by a common sense or by even returning back to whatever we have done. Okay, now for this question, when we are referring to the lesser load, then the answer is going to go for the left column. Now going for question number 6, which is exactly the same figure of question number 5, where you are asked to calculate, okay, where you are asked to calculate the distance, the center of loading at this a distance of how much from the left column. Okay, now we say to avoid the moments, if you remember, to avoid the moments, we need to keep the center of the loading to be the center of the foundation. It means my center of the foundation is at 2.2 and my center of loading is at 2.2. Okay, now if we are referring that this distance is 2.2 and this distance is 1.3, then we can calculate this amount, okay, which is going to be 0.9. Okay, and the other distance, which is represented by 2.2 here. Okay, and this is 1.5, so we have the remaining to be 0.7. Okay, so if you have got your question asking you about the left column, okay, about the left column, then the distance is 0.9 meter, okay, which is this distance. And if we are talking about the right column, then the answer is 0.7 meter. Okay, so that is going to be your answer. Now related to question number 7, we said if we are having with BCC and if we are having without BCC. If you remember, I have given you the values and I have explained them. Okay, and we said clearly that 75 is the value if we don't have a BCC. If we are having a BCC, then it's going to be 40. Okay, and you can return back to your Let me just open it for you. Okay, where clearly it has been mentioned here, and I explained it. Okay, I explained it in the class as far as I remember. Okay, now going for question number 8. Okay, going for question number 8. Now question number 8. Okay, question number 8 says for you that for a combined foundation shown below, okay, a total depth of 800 millimeter. Find the maximum load can be carried by each column, knowing that the safe bearing capacity is 150 kilonewton per meter square per millimeter square. Okay, so in this particular scenario, where we are going to calculate our stress. Okay, our stress is going to be calculated as force divided by area. Okay, divided by area. Okay, and in this scenario, what do we need to have? We need to calculate our force where our stress is given and our area is available. Okay, our area is available. So here it is going to be 150 kilonewton per millimeter square. Okay, per millimeter square. And then we have a force. Okay, and we have an area of foundation given to be 2.6, which is CF2. Clearly it has been mentioned that it's CF2, so 2.6 multiplied by, okay, 4.6 in terms of meter. So now to keep it in terms of millimeter, we're going to say force, okay, divided by 2600 multiplied by 4600. Okay, now cross multiplication. If we're doing cross multiplication, we will know that our force is going to be equal to 2.6 multiplied by 4.6, or let's say 2600 multiplied by 4600. Okay, multiplied by 150. Okay, which will give you, let us return back to our calculator. Where is our calculator? So 2600 multiplied by 4600 multiplied by 150. Okay, which will give you, okay, which will give you 1000 or 1 million. Okay, which will give you 1,794,6 zeros in terms of kilonewton. Okay, now if you want more, if you want to be more precise, okay, if you want to be more precise, okay, what you can do, you can remove the self weight of the foundation. Self weight can be calculated as the length, the width, and the depth, since the depth has been given. Okay, since the depth has been given already, multiplied by 24 to calculate the self weight. So you will reduce the self weight of the foundation to get the total loading coming from the column, and then you will be dividing it by 2 to get your final answer. Okay, now I believe some of the students didn't see the millimeter square, and they have assumed it to be meter square. So in both scenarios, whether you have solved it to be millimeter square or meter square, I'll be considering the answer. Okay, so if we are talking about, okay, if we are talking about, okay, or let me check whether to consider it or not. Okay, so 150 kilonewton, for those who have considered to be 150 kilonewton per meter square, then it's going to be equal to force 2.6 multiplied by 4.6, where our force now is going to go as 150 multiplied by 2.6 multiplied by 4.6. So that's going to be 1794 kilonewton minus the self weight, which has been given as 2.6 into 4.6 into zero point 0.8 as the depth multiplied by 24, which is your unit weight of concrete, since the foundation is made of is made of concrete. So 2.6, 4.6 multiplied by 0 0.8 multiplied by 24 minus 1794 kilonewton. Okay, so it will give you around 1564.368 divided by 2. Okay, dividing it by 2, we are going to get for each column around 782 kilonewton. Okay, so whoever has solved this answer, I might be considering the answer in case of kilonewton per meter square. uh, I might be reducing, I might be giving the full mark. I need to see the answers and then judge. Okay, now going for question number 9. Okay, going for question number 9. Until now, I don't believe we have done something magical that we didn't take till now. Anyhow, going for question number 9, it says for you calculate the relevant loading acting on a foundation, knowing that the ultimate loads coming from the top floors are 1200 kilonewton, 630 kilonewton for dead and live, respectively. Furthermore, check whether the dimensions of the foundation are sufficient or the foundation fails in ground pressure. Unit weight of the soil has been given, and then the safe bearing capacity has been given. Now we need to understand that we said there are there are four loads coming on a foundation. Number one, that is going to be loads from the column. So let's say column loads. Number two is going to be our self weight. Number three, there is a backfill, and then number four, there is a surcharge. Okay, and if you return back to your PowerPoint, okay, if you return back to the PowerPoint, you will see me clearly explaining it here. Okay, and I told you the different types of the loading coming on a column, on a foundation. So okay, so now returning back to our problem. Okay, returning back to our problem. First is columns loads. So it has been given here that the ultimate loading is given. So let us refer to number one, loads from the top. Okay, so we are having a 1200 as dead load, and this is ultimate, so this needs to be divided by 1.4. Live load, which is 630, and this is to be divided by 1.6. Okay, so once again getting our calculator. Okay, we have 1200 divided by 1.4, so we have around 864.2, let's say 29 kilonewton, and then we have 630 divided by 1.6, so we have 393.75 kilonewton. Why I'm calculating the loads in this way? Because you need to compare it later on with the ground pressure, where we need to take the service loading. Number two, that's the self weight, and once again the self weight of the foundation is 24 multiplied by, okay, 24 multiplied by 2.5 multiplied by 2.5 multiplied by 0.3. Okay, so length of the foundation, width of the foundation, multiplied by 0.4, sorry, which is thickness here, so zero point 0.4, and this is going to give you, okay, this is going to give you 60 kilonewton. Those who have considered 10%, they'll be reduced a little bit, because 10% is used to estimate whenever we don't have the foundation dimension. If you're having the foundation dimension, you should be calculating it, and I believe I have explained it. I have explained for you how to calculate the self weight of the different elements, okay, which is a basic fundamental of even previous courses. Number 3, we don't have a surcharge here. Okay, so we don't have a surcharge. There is nothing extra mentioned above the natural ground level. So column loads, self weight, there is a backfill, there is no surcharge. Now going for the backfill, once again using the basic properties of civil engineering qualities, you should know that we need to calculate whenever we are talking about a mass, we are talking about a volume multiplied by unit weight. And whenever we are talking about backfill, we are referring to unit weight of soil. So now we have a volume. Now the backfill when it comes, it will come here. Okay, it means it will cover this particular full area. Okay, so when do we calculate the volume? Volume is an area multiplied by the height. So the height of the backfill is 1.5 meter minus the depth of the foundation. Okay, so this is the height of the backfill, which is going to be 1.1 meter. Okay, so we are referring to the height. Volume once again is area multiplied by height, so 1.1 as a height. Area of the backfill is going to be 2.5 meter square, or 2.5 square, minus 0.3, because whenever there is a column, okay, whenever there is a column, of course there will not be soil. Okay, so multiplied by 2.5 minus zero point 0.3 square. Okay, so 2.5 is the area of the foundation, 0.3 square is the area of the column. Okay, multiplied by the unit weight of the soil, which has been mentioned as 18. Okay. So now if we go and see 2.5 square, that's 6.25, minus 0.3 square. Okay, so let us see how much is 0.3 square, that's 0.09. Okay, so we have 6.25 minus 0.09. This is the area of the backfill multiplied by the height, that is 1.1. Okay, multiplied by the unit weight, which is 18. So we have the total weight of the backfill to be 121.968 in kilonewton. Okay, so now when we add the loads, when we add the total loads, we have 864.29 plus 393.75 plus 60 plus 121.968, and this is going to give you 1440.008 kilonewton. And we say to check the pressure, we need to calculate the service loading, okay, the load in SLS divided by an area. So in this case 1440.008 divided by the area of the foundation, and the area of the foundation is 2.5 into 2.5. Okay, so 1440 divided by 2000, let's say, divided by 2000, 2.5, and then 2.5. So we have the, the loading. Okay, the loading pressure is 230.4, where it's more than the capacity of the soil. The soil can take only 140, so it means that this is failing. Okay, so assalamu alaikum once again. After taking a break, we're going to solve question number 10, and we have solved something similar. We have solved something similar in the previous exam. I mean, in the previous classes. Okay, now if you see, okay, it says for you draw the pressure diagram for the footing with values of well, values with values in both directions for an ultimate load of 300 kilonewton, and furthermore find the maximum bending moments only in the longitudinal side where eccentricity is occurring. Now if you see in this particular. Okay, so assalamu alaikum wa rahmatullahi wa barakatuh once again. We are going to solve the last question after having a break. So the question says for you, we need to draw the pressure diagram for a footing which is eccentric with values in both directions for an ultimate load of 300 kilonewton, and we need to find the maximum bending moments only on the longitudinal side where eccentricity is occurring. Now if you see, we have solved something similar, okay, in the classes. Now the first thing related to the pressure diagram. Now if you notice, we have two directions. This is the first direction, this is the second one. Now in this particular direction, the footing is act or the column is acting at the center of that direction, while in the other direction the column is not acting at the center. Okay, so it's centric in one side, in the other side or other direction it's eccentric. Now if it's centric, okay, we used to have a regular pressure, and the value of pressure is used to be calculated as P over A. Okay, now in case of eccentricity, we used to have of a trapezoidal shape, let's say, where it tends to have more value on the side where the column is leaning. So we are having a value here, we are having another value here, and it goes in this way. And I explained for you how this shape has came. If you remember the PA plus or minus M over Z. Okay, so we said this is going to be P over A minus M over Z, and this is P over A plus M over Z. Okay. Now if you see what we need to calculate the values of B, which has been given A, M, and the Z. So if we go and check the value of B has been given to be 300 kilonewton. Now for me to calculate A is the area of the foundation, that's 2 into 2, so we're talking about 4 meters square. And then we have the value of M, where M is force into distance, or in this case we refer as P into eccentricity, where P is 300. Okay, where P is 300, E is eccentricity, how much we were having the eccentricity for. So if we see, if it's a regular foundation which is concentric, we are having a foundation and a column at the same center, the center of the foundation and the center of the column. Okay. So if this is 2 meters, then this is 1 meter. Now 1 meter actually is to the center of the foundation. So we have 1 meter to the center of the column. So center of the column, center of the foundation is 1 meter. Now if you see, it has been given then 1 meter is to the face of the column. We require to calculate to the center of the column. And you see the distance here, the difference between this distance now, which is 1 meter in the regular scenario, and the actual scenario is 0.15. Okay, as the column side is zero point 0.3, so half of zero point 0.3 is 0.15. So it means I pushed my foundation by a value of 0.15. Okay, I pushed my foundation by a value of 0.15. Now if we zoom in, we will see, that this was the center. Now this is going to be my center. How much is the difference between them? The difference is from 1 to 1.15. So this is 1, which is the regular center, and then the new center is 1 plus 0.15, so that's 1.15. So the difference between the previous one, or the regular centric and eccentric case that we are having, is 0.15 as eccentricity. Okay, so if we return back, to our problem, the eccentricity value is 0.15. Okay, so if we go and multiply, so we have 300 into 0.15, that is 45 kilonewton. Okay, 45 kilonewton. And now we need to calculate z, and we explain that z is bd square over 6, where b is the width, d is the length. So we are talking about 2 into 2 square divided by 6. So we are talking about 8 into 6, that is around, or 8 divided by 6, that is around 1.33. Okay, now if we want to calculate these pressures, what do we need to do? We need to calculate P over A. This is for axial pressure. Okay, that's P over A, which is 300 divided by 4. This is 75. So 75. Okay, now going for flexural pressure, where it's M over Z. So we have it as 45 divided by 1.333. So 45 divided by 1.333, and this is 33.76, let's see. Okay, 33.76, and this is in kilonewton per meter square, and this is kilonewton per meter square. Now if we see here, we have got directly this one to be 75. So this one now is going to be 75 minus 33.76, and this is going to go as 75 plus 33.76. So our values now are going to go 41.24 here, and then the other side 108.76. So we have solved the first part, where we require to draw the pressure diagram with the values. Okay, and that has been finished already, and I believe that you have studied all of these things. Now going for the second thing, where we need to calculate the moment. Now if you see, we have a pressure diagram. They have asked us only in the longitudinal direction where the eccentricity is happening. So we have this shape, where this is 2 meter. Okay, where this is 2 meter, and we have the column here, where this side is 1 meter. This is zero point 0.3, so the remaining part is going to be zero point 0.7. Okay, so the remaining part is 0 0.7. So we have 1.3 and then 0.7, and we need to calculate, if you remember, we need to calculate this part and we need to calculate that part. Okay, now we know the pressure, we know the value of the pressure, that it's here 41.24, and then here 108.76. Okay, so we said, okay, okay, what did we say? We say that we can calculate this particular point. How to calculate this particular point? Let's say that this is point 1. Now this is point 1 and this is point 2. Okay, so if we calculate P1, P1 is going to go as 41.24, which is the regular one, or the base, 41.24 plus, okay, the distance is 1 meter multiplied by the difference here. You can see that we are gradually increasing from 41.24 to 108.76. Okay, so how much is for 1 meter of that particular full distance? So the distance is 2 meter, so 1 divided by 2, half of the distance, where it's 4.1, divided by 2, which is the full distance, multiplied by 108.76 minus 41.24. Okay, which is the difference, or the triangle, okay, which is the triangle height, which is this one. Okay, so now if we see 100.76 minus 41.24, this is giving me, actually, this is giving me 67.52 multiplied by half plus 41.24. Okay, so now we can get the final value. So this one is multiplied by half plus 41.24, so that's going to give you around 75. Okay, around 75. Now going for B2, where it's going to be the same thing, so for 41.24 plus, now the distance is going to go and vary. Now the distance from the base to point number 2 is 1 plus 0.3, so it's 1.3 divided by the full distance, which is 2, multiplied by 67.52, which is this one. Okay, so now what do we have? We have 67.52 multiplied by 1.3 divided by 2 plus 41.24, so we have 85. Okay, we have 85.128. Okay, so now how do we conclude whatever we have done? We have, okay, we have two shapes, so let us draw the column first. So this is my column. Okay, and then what do we have? We have okay, we return back. Okay, we will see that we are having a rectangular shape here, and then after a rectangle we have this shape of a triangle. Okay, if you remember this one, this is the first part. Okay, and the second part goes as rectangle, and then we have a trapezoidal. Okay, a trapezoidal. Okay, now if you see here, if you see here, if we try to concentrate on whatever we have drawn, we will find that this one is 41, 41.24. This is going to be b1 minus 42.24 because b1 is the full distance. Okay. So we have b1, which is 75 minus 41.24. That is going to give you as 75 minus 41.24. This is going to give you 33.76. Okay, 33.76. And then here we can do the same thing. Okay, here we can do the same thing. So if you can see, this is 41.26. Okay, here we have 33.76, which is the same point here, and then we have this point. Now how to calculate this point? This is going to go as p2 minus 33.76 minus 41.26, and this is going to give you 85.128 minus 33.76 minus 41.26. And this is going to go as 10.108. So this point is 10.108. Okay. Now if we start calculating, the moment, okay, if we start calculating the moment, taking into account that this is 1 meter, and taking into account that this is 0.7 meter, okay, we will see, okay, we will see for, let's say, okay, region 1, and this is region 2. So taking into account region number 1, there are two shapes. Okay, there are two shapes. So shape 1, okay, that is a UDL, a regular UDL. Okay, a regular UDL. So what do we have? A shape here. We need to calculate the point load. So how to calculate the point load? The point load to be calculated as 41.24 multiplied by the distance, force into distance. So 41.24, the distance is 1 meter. Okay, and then to calculate the moment, we need to have the distance from the force to the section. So this is 0.5. So it's going to go as 41.24 multiplied by 0.5, or you can use WL square over 2, where it is going to go as 41.24 into 1 square divided by 0.5. Okay, and this is going to give you 42.24 divided by 0.5. 41.24 divided by 0.5, that is going to give you 82.48. For shape number 2, it's a it's a it's a rectangle. Okay, so to calculate the force of the rectangle, we need to use half into base. The base once again is 1 meter into the height. So the height is how much we have got it here. The height has been calculated as 33.76. Okay, and the force will be acting at 1/3 from the right angle, and this is the position where we are calculating the moment. Okay, so to calculate the moment, we can say directly it's a force multiplied by 1/3 of the distance. Okay, from the force to the distance, which is 1/3. So this is going to go and give you half multiplied by 33.76 multiplied by 1 divided by 3. So this will give you as 5.62. Okay, so if we add moment of shape number 1, moment of shape number 2, we have m total as 5.48 plus 5.62, so 82.48 plus 5.62, this is 88.1. Okay, now if you are calculating it for 1 meter, okay, if you are calculating it for 1 meter, we can keep it as the same. If you are calculating the bending or the reinforcement for 2 meter or the width, you can multiply it directly by the width. Okay, both answers can be accepted. Now going for region number 2. Okay, so we have shape 1, which is a rectangle, and we say for rectangle we can use directly w square over 2. So m1 is w square over 2, where w is 41.26 multiplied by the distance, which is 0.7, divided by 2. Okay, so we have the value of m1 equals to 41.26 multiplied by 0.7 multiplied by 0.7 divided by 2. So that's going to give you around 10.1. And then we have m2 for shape number 2. We have m2, and once again it is a rectangle. So this is 1, this is 2, this is 3, this is 1, this is 2. Okay, so we have now once again 0.7 as the length, okay, divided by 2, and then the pressure here is 33.76. Okay. So 33.76 into 0.7 into 0.7 divided by 2. So that's going to give you around 8.27. 8.27. And then we are going to go for shape number 3, which is a triangle. Okay, where this is 0.7. Okay, and we need to calculate at this point. Okay, so the force is equal to half into base, that's 0.7, into height of the triangle. So the height of the triangle is 10.1. Okay, so into 10.108. So the total force is 3.5378. Now the distance between the force to the section, okay, is going to be 2/3. Okay, it's going to be 2/3 of L. Once again, we know it's 1/3 from the right angle, 2/3 from the other angle. So our moment is equal to 3.5378 multiplied by 2 times, or 2/3 of L, that's 0.7. So now we can see, okay, that's 3.5378 multiplied by 2 multiplied by 0.7 divided by 3. So that's going to give you around 1.65. Now if you see, if we keep on adding moment 1, moment 2, and moment 3 for region 2, okay, so m total, it is going to be 10.1 plus 8.27 plus 1.65, and this is going to give me, okay, and this is going to give me, okay, this is going to give me around 20.02 in kilonewton, okay, in kilonewton per meter square. Okay, okay. Anyhow, you just cross check the calculation. Once again, I'm solving using the calculator of the PC. But anyhow, according to whatever we have done. The final moment to be taken into account is this one. If your answer is per meter, if you want to have, this is per meter square. If you're designing for 2 meter, then your final answer is going to go as 88.1 multiplied by 2. That's going to be 176.2 kilonewton. How this is to be frank, this is going to be kilonewton meter per meter length, and this is going to be kilonewton meter. Okay, and that's the end of your test number 1, which I believe you have studied fully, and there was nothing new. Um, and hopefully in the upcoming exams or upcoming tests, uh, you will be doing a better job, and hopefully questions might be a little bit easier, although that I don't feel that these questions are tricky or hard, as these questions, most of them, if not all of them, you have studied them and we have solved something similar. Okay, so best of luck and see you in the upcoming lectures, hopefully.